be $1,000 upgrade to this one. Is that $1,000 actually worth it? Well, that's exactly what I thought as well, until I looked underneath and actually realized that the upgrade is not as bad as you think, because there's a lot of free things that you would have to pay for the Air anyway. And depending what you do, there's a laptop for each of you. You don't necessarily pay more, but you also get more. Or do you? Let's find out. This is not a sponsored segment, but I thought I'm going to tell you about this device because if you're interested in this video, you'll probably want to know about this because this changed the game. This finally allows us to have as fast storage speeds externally as you would get internally. This changes the game, and this finally allows us to not pay the Apple storage tax. If you don't know what I'm talking about, go check out our video in the video description below. If you want to check out my video on the MacBook Airs and which upgrades are actually worth it, go check it out. I bought every single version, as you can see over here, so you don't have to. If you would like to pick any of these up, or you're actually on the look for a laptop and you want to purchase any of these, I've got some links in the video description below. If you go through them, you'll get them cheaper than on Apple's website.
That's right. You decide.
I do get a small commission, but at no extra cost to you, but that does help the channel and the helpful content coming your way. Let's take a look at the 13-inch versus the 15-inch MacBook Airs. What exactly do you get extra? There is a $200 difference between the base 13 and base 15. Is that $200 worth it? What exactly do you get for it? Well, actually, there's some good news. The 15-inch actually is better bang for your buck than the 13-inch. Let me explain. Firstly, you get a free 70-watt charger with it, so you get now quick charging, which on the 13-inch you would have to pay $20 extra for. Secondly, the 15-inch MacBook Pros come with the free $100 GPU upgrade. The 13-inch base model comes with 8-core GPU, whereas the base model 15-inch actually has fully binned 10-core GPU and 10-core CPU. So you get extra 2 cores on the GPU. So now we're actually getting extra free $120 worth of upgrades from 13 to 15. Plus on top of that, we get obviously the bigger screen and a little bit of a bigger battery, but the battery drive roughly is the same because of the bigger screen, obviously. But also because of the bigger chassis, the performance is going to be slightly better on the 15-inch because it's better at dissipating the heat rather than the 13-inch. The 13-inch can throttle very, very quickly if you do heavy tasks, but the 15-inch not so much. So all in all, the 15-inch is actually a better bang for buck because your upgrade from 13 inch to 15 inch is actually $80, not $200, because the rest of the things are kind of free, what you would have had to pay for on the 13-inch upgrade. But then let's put the 13-inch on the side and look at the 15-inch MacBook Air, which is one of my favorite models actually. Should you get the 15-inch MacBook Air or the 14-inch MacBook Pro? The base model of 15-inch to the 14-inch, yes, there's slightly smaller screen size, but there is a $400 upgrade. $400 for this. What exactly do you get? Because the chip inside is the same, M4 to M4. Nothing changes there. Well, Apple actually gives you a free $200 SSD upgrade. Now you have 512 gigabytes instead of 256. So that you would have had to pay for on the MacBook Air. Suddenly, our upgrade is going to cost only $200. For that $200, we also get a lot better screen. The screen now is 120 Hz instead of 60 Hz. It goes a lot brighter. It has more pixels. Everything's better on that screen, which is really nice. So if you use the Pro version, you'll see everything seems a lot snappier just because you've got more refresh rate, so everything feels a little bit more fluid. You get better ports. You get HDMI port. You get SD card slot and extra. USB-C port, which is Thunderbolt 4. So one extra Thunderbolt 4. So if you're doing a lot of presenting, for example, and you want to just plug in HDMI to your laptop, having no dongles with you as a MacBook Air user on the Pro, it is a very welcome upgrade. The Pro also comes with active cooling, which means that your M4 performance now is never going to go down. It's never going to be throttling because that new active cooling is able to keep it on the wraps all the time. Whereas the Air will throttle if you do heavy loads on it. So if you're planning to export things or still do a little bit of video editing and exporting some stuff, it will be faster on the Pro version just because it's got active cooling. Potentially, it's actually got a little bit of a better battery life because it's a little bit thicker and you can put a little bit bigger in there. And a faster charger is also available. This Pro versions can charge the battery at up to 96 watts, whereas the Air can only go to roughly about 70 watts. So now, in essence, this is a $200 upgrade that you pay for better ports, better screen, better charging experience, faster. So is that worth it? Now the question is, what if we upgraded from the 15-inch MacBook Air to the 14-inch MacBook Pro that's got the M4 Pro chip? Now that is extra $800. Is it actually worth it? Firstly, you get two free upgrades with it. You get a free SSD and then RAM upgrade. So that costs $200 each on the MacBook Air. From 16 gigabytes of RAM to 24 gigabytes of RAM to 256 gigabytes of storage to 512 gigabytes of storage. Now the specs that you get with the base model is actually only $400 upgrade. You do get a lot better CPU and GPU. You get extra 2 CPU cores and extra 8 GPU cores on the M4 Pro. But how much better is the M4 Pro compared to the M4? Oh my goodness. If you do any creative tasks, especially video editing, we're talking 50% CPU performance. That's pure CPU performance. Only 2 cores extra to 12 cores, but the CPU performance multi-core is 50% faster. If you don't believe me, go check out my all Mac Mini comparison where we compare the M4 to M4 Pro Mac Minis. There's a huge performance jump from the M4 to M4 Pro. The GPU, pure GPU performance, the extra 8 cores are 60 to 70% better. So if you are doing any Blender, any GPU heavy tasks, it's going to be absolutely massive. With the M4 Pro, you also get better media engines inside there, and that is going to give a huge performance for video editing. We're talking about 70% increase in video editing, for example, in Premiere Pro from MacBook Air to MacBook Pro. In fact, even more because the M4 would be throttling because of the not active cooling, whereas the Pro would just run all the time. So we're talking up to 2 times faster video editing performance, but in average, in overall scores, we're talking about 70% increased video editing performance in Adobe Premiere Pro from the Air to the Pro. That is absolutely massive. Then on top of that, obviously, we get better ports, the same ports as we mentioned previously, but because it's the M4 Pro, now suddenly the Thunderbolt ports are not Thunderbolt 4, but now they're Thunderbolt 5. So if you need Thunderbolt 5 and you want to extend your storage or something like that on a Thunderbolt 5 device, the Pro chip will give you that chance. So in essence, it's not an $800 upgrade because some of these things are already, upgraded or you get for free when you go in higher. So that $2,000 laptop now is actually a $400 increase from the M4 MacBook Air. To me, that $400 increase is a huge performance gain as a creator. So for you, if you're doing content creation and you're wanting to do video editing, then that $2,000 laptop is absolutely insane. By the way, if you check out my links below, you should be getting this for around 10% off. So that's around $1,800 if I'm not mistaken. Go check out the links in the video description below. Hopefully that deal is still going when you're watching this. And now suddenly it starts to make a lot of sense. So who are these laptops for? Which one should you be getting? I think if you're doing just basic tasks and you're taking notes and you want the laptop to be extremely light and very small and still have incredible, web browsing performance, the 13-inch is the absolute amazing pick for you. Going through the links below, you should get this cheaper than $1,000. If you have extra $200, I think the 15-inch is a better value for you. I feel like you're getting a better experience in this. I prefer larger screen. It's still extremely thin and really nice to use. It's fantastic and I really enjoy that. If you're thinking that you're going to be doing a lot of video and photo editing on the MacBook Air, I don't feel like this is a best option for you, especially if you're in a hot climate where there's more than 30 degrees outside, 25 plus degrees. The M4 is going to start to throttle on the MacBook Air a lot doing video and creative tasks because it doesn't have active cooling. Then you want to go with the Pro, and then going with the Pro, I'd kind of say that if you're doing any creative tasks, going with the M4 Pro is going to be a huge upgrade for you. If you just want a basic laptop that still is really nice to use in terms of usability and some of the ports on the screen, but you don't actually need the extra performance, then going with the M4 model makes sense for you. And I get it. Content creation, go with the M4 Pro. That's the one that makes the difference. If you want to pick any of these up, the links are in the description below. Thanks, guys.
Recording in
And I'll
progress.
pick some problems from section 5.7. So let me see, I'll share with you at once. There, and then there, and some note for us at once. Let me see. Okay. There. Lecture 1, week 12. Math 2305. Spring 2025. Right there. So I'll put a problem right here. It could be this. They give you a recursion. Let me see. Oh, can you hear me well? Just checking. Perfect. So let me stress that. Section 5.7. There. So ways to try to find a closed form for a recursion. Try to find a formula. So here it comes. They give me something like this. Let right there AK be equal to 3 AK minus 1 plus 1. Right there. And this is for integers greater than or equal to 2. For K greater than or equal to 2. And of course, K are integers. Like that. I can even say C plus. Right there. And the initial condition, A of 1 equals 1. Right there. And what's the question? Find the closed form. That's recursive. So you need to find a formula where we can jump anywhere we want to in that sequence. For example, right, so here I will say find an explicit formula. Find an explicit formula. By that, they mean an ordinary sequence, not a recursive sequence. Find an explicit formula. Let me put it in parentheses. A closed form, comma. We can also call it a solution. To the recursion. Find an explicit formula to the recursive sequence above. To the recursion above. Perfect. We'll end up with a guess, and then we'll need to prove it by induction. Can you see? The problem is long. The first part is Play with the numbers and try to find a guess, and the guess will be just proof that it actually works in a proof by induction right there. So we're going to do recursion, or we're going to do what computer scientists call it plug and chug. We're going to do plug and chug with this. Okay, so I can start solution right there, solution. Right there, A1 it's equal to 1. A2. So I call this one plug and chug forward.
You can get $0 delivery fees on.
Let me see, I'm admitting some students. Plug and chug forward right there, because you can see I'm moving from A1 to A2 to A3 and so on. A2 is 3, A1 plus 1, and we know that A1 is 1, so I will plug in 1 for A1. Sometimes I need to see if it's better to reverse them. Here is reverse them, it's an addition. So I could potentially write them like this. Right there. So perfect. That's my first step. Do you agree with my first step? Perfect. So next. Of course, let me do this also. That is 1 plus 3 times 1 right there, because A1 is 1. Can you see I made all those moves? Just in case I reverse the order. A3 it's equal to 3 A2 plus 1. Can you see what I've done? That's the format, is the previous one right there. 3A2 plus 1. I'll reverse it just in case, because it's additive and I have there commutativity right there. But what is A2 equal to? All of this right there, all of that. So then I will do this. There comes the plug. Can you see? I just plug in A2 from the previous one right there. This is a math that maybe you've never done before right there. This is the math of recursion, and it's very important for computer science. So I just plugged in. Now I'm going to proceed to chug. This is chug. Switch it a little bit so we can get an insight on the pattern. That's the meaning of chugging. Here it comes. I just plug the A2. For A2, I plug the previous information right there. And now I'm going to do some chugging. Did you see my chugging? Right there. I distribute. It was only to distribute, but we call it chugging right there. And can you see that I got a little bit of a pattern? Can you see that I have a pattern? 3 to the 0, 3 to the 1, 3 to the 2, right there. A3 is 3 to the 0. 3 to the 0 is 1. 3 to the 1 is 3. And 3 to the 2 is the 3 to the 2 right there. Let's take a look at A4. A4 is 3, A3 plus 1, right there. But since I know it's going to grow, I'm going to swap the order. So swapping the order was important. Right there. Can you see? I swapped the order by its additive and its commutativity under addition. And now comes the plug. Let me do the plug in color. That's going to be the plug right there. I'm putting the A3 for A3 right there. And then I'm going to chug. That's plugging. Plug. And let me, of course, do the plug. So A4 is right there. And that's it. Distribute. Right there. And this is A4. Right there. Let's do one more, A5, and I think I have the pattern. But I see the pattern. Right there. Let me see. A1. Well, let me see the pattern right here. I highlight. A3 is 3 to the 0, 3 to the 1, 3 to the 2, 1 less. A4 is 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, 1 less. Right there. Let me just, I'm thinking that I have a pattern already, but I'll check it with A5. There, 4, 1 less. My guess right now is that for A5 is going to be 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, and 3 to the 4. 1 less right there in that sum. I'm going to check it right now, but that's my guess right there. Let's do it. And then we have a formula for that. We have a formula for that sum right there that we proved by induction. So we are going to use that shortcut, that formula right there. Happiness with that. So let me check it now that we get that. So let's play with it. A5 algebraically, plug and chug. So A5. I'll take a look at the series, at the sequence. A5 is, I'll put the 5 right there. There is going to be the 1 less. 3 times A4 plus 1 right there. So perfect. A5. Oh, it's not moving. Okay, there, A5. A to the 4. Oh, 3 A to the 4 plus 1. 3 times. There. We swap the order. And that was just a feeling that it was going to grow in that direction. So here is the A4. And all of this is the A4. So I'm going to put it right there. I'm going to put the A4 right there. And I'll do some, that's the plug. So A5 is a 1 plus 3, open parenthesis, 3 to the 0 plus 3 to the 1 plus 3 square plus 3 cube. And then that was the plug. Let me call it plug. And now comes the chugging, which is in this case, chugging is only distribute. It's an easy problem. I don't have to do some complicated chugging. A5 is 1 plus 3 to the 1 plus 3 squared plus 3 cubed plus 3 to the 4. So if I were to write it nicely, A5 is 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4th. It checked. Now, let me erase here. It checked. 5, 4, and powers of 3. So now, we have a formula. AN, we use the nth notation instead of the kth notation for the guess. So the nth term of the sequence in the solution is going to be 3 to the 0 plus 3 to the first power plus 3 to the second power plus all the way to 3 to the nth minus 1 right there. One less. And that's the guess. That's the guess right there. So can you see how we fought for the pattern with plug and chug? And now we have a formula in section 5.7. Let me tell you which page. It's a formula that we already proved. The formula is on page 345. So let me write that formula. That is important for this section. So I'll write it in red. In green, right there, formula. The formula says 1 plus r squared plus powers of r from r raised to the 0 all the way to r raised to the n is equal to r raised to the n plus 1 minus 1 over r minus 1. So let me circle the formula. Make a little box. And of course, r cannot be equal to 1 because you have an r minus 1. But can you see, we have the powers of 3 right there. But it's going to 1 less, 1 element less. So now I want to utilize that formula. We can see that AN is equal to 1 plus 3 squared plus all the way to 3 to the n minus 1. So this better be equal to what? If I utilize the formula.
3 to the n plus 1 minus 1 over 2.
Oh, okay. And then I cannot hear you. Okay with that. So my headphones are not working. They're fake. So no problem. I'm taking out. They're fake headphones. Okay. I'll take them out right there because I hate you from. Okay. So Ansley, what are you?
It might be because my laptop's on a fluffy blanket. Can you hear me now? Oh, no, I can't hear you.
Can you hear me now?
Yes.
Oh, I'm sorry. Okay, this is really weird. I can hear you from outside my headphones. But if you can hear me, that's what matters, that you can hear me right there. But let me hear you too. What was your answer? 3 to the?
3 to the n plus 1 minus 1 over 2.
Oh, okay, but look, okay. Look at that one. That one is going all the way to n. This one is going all the way to n minus 1.
Oh,
See, you see, that one is going all the way to n, and here you have an n plus 1. So this is going to be,
just n.
yes. 3 raised to the n minus 1 over, of course, 2. Right there. So can you see how it maps right there? How the pattern goes right there. That's how we utilize the formula. And now we have a legit guess right there. It's an ordinary sequence and it's the closed form and it's an and is 3 raised to the n minus 1 over 2 right there. So, and that works for all n in the natural numbers right there. Let me see here for all n in, let me check. This started at 1. And with the 1, we get a 4. So here we're going to start at 1. There. But let me check I just need to see where to start with this one. Here we started with 1 and we got 1. A1 is 1. So here we're going to start with 1. And in C+. If I plug in a 1, I get a 2 over 2. And a 2 over 2 is A1. Let me just check it. I have, there is the guess. Here is the closed form. So here is the solution to the recursion. An explicit formula. Closed form. A formula. And the recursion was AK equals to 3 AK minus 1 plus 1. And this was K greater than equal to 2, integers. And A1 was equal to 1. So these are equivalent. Not yet, I need to prove it by induction. They are equivalent. Right there. One is a recursive definition. The other one is a sequence. Right there. So I still need to do induction. Right there. I just did it by pattern. That doesn't mean that could work. I need to check by induction. That I need to prove it. So, but again, this is the recursion. Recursive sequence. And the above is just an ordinary sequence. We can check the first few terms just for fun. So we know, let's plug in some terms on the recursion. Right there, the first element is 1. The second element is 4. Check me on that. The second element is 4. The third element, what will be the third element?
13.
13, yes. And so on. Right there, perfect. And so on. Now, let's check on the formula. What's the on the closed form? Explicit formula. It has so many names that becomes confusing. When I plug in 1, I get 3 raised to the first power minus 1. So it's a 2 over 2, and that's a 1, comma. When I plug in a 2, it's a 9. 9 minus 1, it's an 8. And an 8 divided by 2 is a 4. Right there. When I plug in a 3, it's a 27. 3 raised to the third, it's a 27. Minus 1, it's a 26. And the 26 divided by 2. And so on. I do not know that they are going to be equal. I'm just checking a few terms. Now I need to do a proof by induction. So that's it. I finished the first part of the problem, which was recursion forward, right there. And now I need to do induction, right there. So induction to check for correctness of the guess. So here it comes, part 2. We need PMI to check for the correctness of our explicit formula. To check that the elements of the recursion, that's what I started with. To check that the elements of the recursive sequence satisfy the explicit formula. Right there. So I'm trying to explain it because sometimes it's confusing what we're trying to do. So we started with the recursion. So that's it. Here we have show that elements from AK equal to 3 AK minus 1 plus 1 for K greater than equal to 2. And of course, K in Z or C plus, comma, with initial condition A1 equals to 1, satisfy the formula, and the formula Susana uses N. And again, I mentioned that last class. That is a super cool notation wise. It's super cool. So a N equal to the formula that we had. The formula that we had was divide by 2, 3 raised to the N minus 1. Let me write it in full splendor, a little bit bigger. There. A N 3 raised to the N minus 1 over 2. Perfect. PMI. Right there. Proof. Right there. By PMI. Right there. Let Pn be the predicate elements of the recursion satisfy the formula. Satisfy an equal 3 raised to the n minus 1 over 2 and close. When I'm saying elements of the recursion satisfy the formula, I never said all of them. So I'm not saying for all. If I say for all, it's not a predicate, it's a statement. So leaving the quantifier out is just a way to just construct this predicate right there. It's some of them. I never said all right there. We'll show that it works for all. So here we have perfect. It's an open sentence right there. It's a predicate. So now we go for the first part of induction, right there, base case. Base step. Right there. Show P of 1 holds. P of 1 is true. Right there. So the first element of the recursion. The first element of the recursion is 1, comma, and 3 raised to the 1 minus 1 over 2 is 2 over 2, which is 1. So the first element of the sequence satisfies the formula. When you plug in 1 on the formula, you get the same element. So thus, P of 1 is true. Right, perfect. Inductive step. Any questions on the base step? Are you happy on the base step? They're one and the same. The first element of the sequence recursion is mapping, is just, it's the same as the plugging 1 in the formula. So now comes inductive step. Perfect. Inductive step. Show that P of K implies P of K plus 1 for all K in C plus is a true statement. Show that that implication is a true statement, that the algebra continues right there. If I can show that that is a true statement, then I can invoke PMI and we can go all the way to infinity with this. Okay, with that, we want the axiom to take us all the way to infinity. Happiness with that? Perfect. So that's it. Assume uh, 1 plus 3 plus 3 squared plus. Oh, I need to go and get my cable. Right away. I'll be back. Perfect. Right there. So assume that 1 plus, oh, let me see here. I'm just daydreaming. Assume that 3 AK 3AK plus 1. Let me see. The sequence is 3AK plus 1. Yeah. AK, which is equal to 3AK minus 1 plus 1. Assume AK, which is equal to 3AK minus 1 plus 1, satisfies um, 3 raised to the K minus 1 over 2. Right there. That's the formula. So assume that. Now, consider and now you're going to consider the next. The next one is 3 of K plus 1. So right after the consider, let me take all the way up here. Right after the consider, I go all the way up here. Right after the consider, you replace and you put right here a K plus 1. And here you put a K right there. That what comes right after the consider. Let me put the note right here. Put a note. After consider below. And that's always the case. So let me see. Now, and that's for the proof. We already finished with getting that guess. But now for the proof. So consider AK plus 1, which is equal to 3 AK plus 1. But now, by inductive hypothesis, you can change this. By inductive hypothesis, you can change this by this. Right there. You can change by inductive hypothesis. So I'll say right here. We get, and then after that, we'll do algebra. We get AK plus 1. It's equal to 3 raised to the K minus 1 over 2. Right there, plus 1. There. And then we'll do all the algebra. But at the end of the algebra, right here, we should get 3 raised to the K plus 1 minus 1 over 2. Right there. When we finish all the algebra. Right there. That's the final outcome. And that means that the property continues. Right there. That it continues satisfying that closed form. So let's do the algebra. So we're going to distribute the 3. Let me do it, make it bigger. So this is the final step. It's a 3 times a 3 raised to the K minus a 3 divided by 2 plus 1. So I'm enjoying the algebra step by step. And then let me continue put that outcome that we want. Here we want the outcome to be 3 raised to the k plus 1 minus 1 over 2. Now, this will become 3 raised to the k plus 1 minus 3 over 2 plus 1. Now, let me keep moving this one down. And that will be the last time. This is 3 raised to the k plus 1 minus 1 over 2. So now the next one, we're going to add the fractions. This is 3 raised to the k plus 1 minus 3 over 2 plus 2 over 2. Right there. 1 is a 2 over 2. And I'm sorry, I promised that was going to be the last move, but I'll move it again. Right there. I'll put it here. 3 raised to the k plus 1 minus 1 over 2. This next step, common denominator. And then you're going to have a 3 raised to the k plus 1 minus 3 plus 2. So that's it. We get the final outcome right there. It does. It just continues. So what I'm going to say, thus P of k implies P of k plus 1 holds is true for all k in C plus. Right there. So by mathematical induction, by PMI, comma, Pn, the predicate is true for all n in C plus as desired. Right there. And then put the box. So the problem is long. It has taken me 40 minutes right there because, of course, I talk around the problem like that. It should be shorter. It should be around half an hour, the problem right there. But it's a recursion where I fought for a pattern and then I check that the pattern is true by induction right there. That's a problem that happens a lot in computer science because you are going to start with an algorithm, with a game. The game is recursive, and then you are going to make a guess to be able to go anywhere in that recursion. The formula, the explicit formula, takes you anywhere in the recursion. Okay with that? Okay, let me see. Let me go all the way to the top, right there. So the recursion is a function of time. So it's running through time right there. Like we do. We run through time right there. And we get older and we run through time. So the explicit formula that we got right here, the explicit formula that we got right here. So this one, let me grab it. I'm trying to create an analogy. I'll put it right here. So the recursion runs through time, and you need to do a step by step like a computer loop. My pen just ran out. I just created a super cool analogy. Okay, with that, yeah. Let me choose. I need 4 Mississippis. So I'll write the recursion. Anytime you have a recursion, it's running through time, and you pass through the years. Right there. So let me see. The recursion that we had, AK equals to 3AK minus 1 plus 1. There for all K greater than equal to 2, and this recursion was born in A1, which is equal to 1. If I change the initial condition, I change the recursion right there. The explicit formula is a time traveler. The explicit formula it's a time traveler. Is a time traveler. It jumps around time, around the subscript, time traveler. Right there. And we got it. The time traveler is the AN equal 3 raised to the n minus 1 over 2. Right there. Okay, how did I get the analogy? Because I was just thinking of a time traveler from Argentina. 1957, there is a comic that is called El Eternauta, and that's the hero of the Argentines of 1957. The comic is like your iPhone in 1987 for the Argentines. It's a cheap way to just relax and get to know. So here it comes. They're going to come up with a Netflix show, Eternauta. It's an electrical engineer. And aliens are attacking Buenos Aires. So the person that created this, which is Osterfield, right there, is an alien attack in Buenos Aires. Nothing make him feel just comfortable about the city. It happens in places that they walk every single day, right there. So that's it. There, but it's really cool. He's the hero. I'm sorry, he's not the hero. The hero is the physics professor, right there. Okay with that. So perfect. The explicit formula is a time traveling, and if I want to go to the 400th element of this loop, I can actually plug in. I can plug in, or to the 10th element, I can plug in the 10, and it will be, I will go to the 10th year automatically, just like El Eternauta, over 2. The other way, with the recursion, I need to go term by term, all the way to the 10th term, because I need the previous one to get the next one. So the explicit formula comes to the rescue, right there. Did the analogy work or not? I'm sorry, I just got the news that it was going to be a Netflix show, and it was just, they just came out with a movie right there. It's many episodes right there of this one. So, perfect. Okay, let me see. Let's take a look at another one right there. I'm looking at the problems on the back of right there. Oh, let me give you something that will make it look like a project, like will make it look why we will do this. So here comes another example. This used to be an interview in computer science back in the 80s. They give you the first element right there, and they tell you that that element is called T1 right there. So that's one computer, and it's T1. Let me tell you what T2 is. T2 is 2 computers connected by a network right there. And this is T2 right there. T3 is that. So here is T3. So T1 is equal to 0 because you're counting the number of edges. and there are no edges. What is T2 equal to? Well, I was going to write it down. T2 is equal to 1. There is one connection between those two terminals right there. What is T3?
3.
3. Then we want to find T4. T4 is 4 terminals and all the edges that will connect 4 terminals right there. So what number I'm going to have for T4?
6.
6. Gracias. Yes. 6 is 1, 2, 3, 4, 5, 6 right there. And I made him trembling because it looks cooler. It looks cool right there if I just make him a little bit trembling right there. Happiness with that. So next, we want to find T5. Next, we want to find TK, the recursion right there, the recursive sequence. Am I able to come up with the number of edges in terms of the number of edges before? Can you see what I'm saying? I need to come up with something that will count the number of edges from the number of edges before. So I want to be able to compute. I'll do it here. So jump on the recursion. I want to be able to compute T5, not by making T5, but by thinking of T4 right there. So compute T5, and that will be a recursive computation, a recursive reasoning. So recursive reasoning. Right there. Get T5. But by thinking T4. Right there. This is how it's done. I want T5. Those are the number of edges when I have 5 terminals. I already have T4. What else can I do to T4 to be able to get T5 right there? Can you see what I'm saying? I already have T4, so T4 is going to be part of the formula. What do I need to do? What do I need to add to T4 to be able to get T5?
You need to add a vertex.
I will add a vertex, and that vertex will be connected to all the previous terminals. So yes, I'll say right here, that's perfect. I need to add a vertex. I need to add a terminal. I need to add another computer because it's T5. Let me say we need to add another vertex. Comma. That vertex will connect to all the previous vertices. Okay, with that vertex better connect to all the previous vertices. Let me say it. The new vertex, this new vertex must connect to all previous vertices. right there. So what better be that number that you put that new vertex and it must connect? How many more edges I'm going to get right now to be able to get T5?
The new vertex is going to have 4 edges.
Yes. Let me make the picture. Yeah, I'll make the picture now, but we've done the reasoning. There we have T4. So here is T4. Somewhere here, I want to put it above in green. Is going in red is going to be the new vertex to try to assemble T5. I'll put it here. And then all of this are going to connect right there. So it's going to be a +4. No way out. I'll put it in green. A +4 right there. But now, what's going to be TK? Because now I want to do it in that direction. What's going to be TK equal to?
TK minus 1 plus K minus 1.
Yes. -1 right there. And that's a recursion. And we start at T of 1. What is T of 1 equal to above? T of 1 is 0. That's it. This is a recursion. So perfect. We are done with the first step. So that was a problem in computer networks. They wanted to know how many edges to connect all the network, all the computers. Okay, without the old way, by a cable. Right there. You want to connect all the computers in the network by a cable. So that was an old problem from the 80s, right there. Now, this is the recursion. What am I dying to have right now that I have the recursion? An explicit formula. Find an explicit formula. By plug and chug. Right there. And what do we have to do after doing the explicit formula by plug and chug?
Prove it by induction.
Induction police. Yes, the induction police needs to come right away. Okay, with that, can you see that the problems are long? So the computer scientist, by the time she gets to induction, she's exhausted. Right there, because she had to play the game. The game was recursive. After that, she had to do plug and chug. And then after that, a little check by induction. Make sure that it works forever, right there. So perfect. So let's go right now and play some plug and chug to see what we get right there. Sometimes you just get it by guessing, but let's see right there by guessing without doing so much plug and chug. But let's bring the plug and chug. So we start right here. Let me see. Plug and chug. T of 1 is 0. T of 1 is 0. T of 2. T of 2 is equal to T of 1 plus 1 minus 1. A T of 1 plus a 0. Oh, I'm not going to go anywhere. There. Okay. There. Let's go to the next one. T of 3 is equal to, and then is equal to T of 2 plus a 2. Right, and I'm sorry, this is a 1. T of 1 there, if I follow that pattern, that's a 1. Typo right there. So T of 1 is 0. So this is equal to 0 plus 1 right there. And this is equal to T of 2. T of 2 is 1. And then there I have a plus 2. Next, T of 4. T of 4 is T of 3 plus 3. But T of 3 was 1 plus 2. So it's a 1 plus 2 plus 3, which is equal to 1 plus 2 plus 3. One more. T of 5 is T of 4 plus 4. But T of 4 is all of this. 1 plus 2 plus 3. So we have the plug. 1 plus 2 plus 3 plus 4. And then we drop the parentheses. It's equal to 1 plus 2 plus 3 plus 4. Right there. So that's it. Let me check the pattern. Let me use a highlighter. 3 ends up in 2 with the sum. 4 ends up with 3. 1 plus 2 plus 3. 5 ends up with 4. So we are very confident that T6 is 1 plus 2 plus 3 plus 4 plus 4 plus 5. Right there. So we can check it. Check. T of 6, it's equal to T of 5 plus 5. But T of 5 was 1 plus 2 plus 3 plus 4 plus 5. So it works. It works right there. T of 6 goes all the way to 5 right there. So now we'll go for T of K. T of K has to be equal to
TK minus 1 plus K minus 1.
yes. But now on the recursion, yeah. TK will be equal to 1 plus 2 plus 3 plus 4 all the way to K minus 1. Right there. So that's it. We have that explicit. We have that explicit right there. So, but we have a formula for this from our previous classes. Formula 1 plus 2 plus 3 plus all the way to the n is n minus 1 over 2. That was the first formula that we proved by induction. right there. Right, of course, that works for all n's. Right there in C+. Right there. So what's going to be TK?
So k minus 1 times k minus 2 over 2.
Okay. Let me see. Yes. K minus 1 times k minus 2 over 2. Yes. Because this formula goes up to n. And then right there you get the nth term. And there you get one less. So go to your last term and then one less, multiply by one less and divide by 2. So perfect. Go all the way to your k minus 1. Then multiply by one less, k minus 2, and divide by 2. Perfect. This is a potential explicit formula. We need to prove by induction that works. So this is a guess. Right there. So, but is the candidate? Is the candidate to be the time traveler? To which one? To the recursion that we had above, right there. So that is the time traveler, this TK. And of course, I'll put for the recursion TK minus 1 plus k minus 1. And then right here is for k and t of 1, it's equal to 0. And k is greater than equal to 2. Right there, of course, integer. So here is our recursion. And right here, I'm going to put our potential guess. In the flavor of Susana, I'm going to use the nth notation. So just following Susana, n minus 1, n minus 2 over 2. And this is for all n greater than equal to 1 in C+. For all n in C+. Right there. Let's check if some terms are the same. Right there. We know from above that we were getting these terms. We were getting 0, 1, 3, 6. 0, 1, 3, 6, 10, because T5 is 10. 0, 1, 0, 1, 3, 6, 10. 0 by the recursion. 0, 1, 3, 6, 10, and so on. So let me check now for this one, for our short form. When we plug in 1, we get 0. When we plug in 2, we get 1. And I'm using the time traveler right there, the closed form. When we plug in, let me plug in 5 because it's a time traveler. So I should get a 10. So when I plug in 5 is 5 minus 1 times the 5 minus 2 over 2. I cross my fingers that I will get a 10. So that will be a, I hope I do. Let me see, that will be a 4. T5 gave me a 6. Let me see. That's the wrong time traveler by a year. Let me check. It's a 4 times a 3 over 2. It's a 6. Let me check T6. T6 is 6 minus 1. Is 6 minus 2 over 2. That is 5 times the 4 over 2. That's a 10. So let me check right here. We started with, I'm calling that one T6. So let me check all the way above. Did I skip a number? Oh, there, 1, 2, 0, 1, 3, 6, 0, 1, 3, 6, 10. And this is T of 1, T of 2, T of 3, T of 4, T of 5, right there. So I'm off by 1. And I can see why, right there. Goes all the way to K minus 1, K minus 2. There. So the formula, let me check the formula. It should be, let me check this. K n minus 1 over 2. Oh, I'm sorry, when I wrote the formula, sorry about this. When I wrote the formula, I was thinking of the time traveler. It's n plus 1 over 2. The formula is n plus 1 over 2. So for us will be k minus 1 times k over 2. I'm sorry about that. That plus in your notes. So put a plus right there. So this becomes k minus 1 times k over 2. So this becomes n minus 1 times n over 2. So now it will work right there. So that was really nice that I checked. So let me see. Yeah, let me try T5. T5 will be the 5 times the 4 over 2 to give me the 10. So thank you. Checking right here. These ones show me that I was wrong. Right there, the check. So that's it. Now I have it. That is the correct, this one. Let me circle it. This is the correct explicit. I'll put it here. The time traveler. Tn, it's n. Well, n minus 1 times n over 2. It's the same, it's multiplicative. n minus 1 over 2. And this is for all n greater than equal to 1 in C+. Let me write it. In C+, right there. So perfect. Let me circle it and I'll give you super freedom right there. There is the correct explicit. We still need to do induction. Let me say it right here. Note well. we need induction. We need PMI to check for correctness of the guess. It would have told me, PMI would have told me that I was wrong. Can you see? I made a mistake. And then PMI would have told me, you are wrong. It would have not checked. So perfect. Now I know I'm correct, but I still need PMI. We need PMI to check for correctness. It works for both. It checks for correctness, but also it checks for lack of correctness. So that's really nice. We need PMI to check for correctness. Of guess. Guess by plug and chug. Of guess, I'll say it, by plug and chug. Right there. Thank you. Super ultra freedom. Super ultra freedom. I'll keep doing some of these problems. Right there. Any questions? Any questions?
Earlier, for an earlier proof, you used the formula to get an element from the previous element instead of the recursive sequence. Are those two things interchangeable?
Oh, okay. Can you repeat the question? Can you repeat the question?
Yes. So earlier, it was specifically for the problem that said show that elements from AK equals 3AK minus 1 plus 1.
Yes.
Yeah, it's the formula that looked like 3 to the n minus 1 over 2.
Yes. Right here.
Under the inductive step, when you said assume AK, yes, right there. You just went past it. If you scroll up just a little bit more, right there, yeah. So you said AK, assume AK is equal to 3AK minus 1 plus 1 satisfies that formula. Is there a reason why you used AK equals 3 AK minus 1 plus 1 instead of the sequence, the recursive sequence?
Oh, okay. I am using the recursive sequence right here. Let me circle it. Right there. All of these put together. Let me circle all of this. All of these put together. Right here. All in blue. All that stands for P of K. Right there. Because I need to assume P of K with the satisfy right there also. That means P of K because P of K is the kth element of the recursion satisfy the formula. Let me put it here. PK is the kth element of the recursion satisfies the closed form. Right there. Did I answer the question or not?
I'm processing, sorry.
No problem. Because I need to assume the pkth to be able to show the pkth plus 1.
Yeah, that makes sense.
And we did an example like that. Let me see. We did an example like that in section 5.4. Let me go to the textbook to that example. And that example was let me see. I'll just put it right here. Proving a property of a sequence. Oh, that's with a strong induction. No, section 5.3. We did it in section 5.3, and let me go to it. 5.3. Oh, I'll put it right here. Example. .33. Right there. on page 295 for the students that have access to pages. Right there. And that one, on that example, perfect. On the second page, she is, Susana right there is doing exactly what I'm doing right here, assuming the PK right there.
Yeah, okay. I think I understand. I think I just had a misunderstanding of
No problem, no problem. Yes, yes, yes. And then of course, showing the PK plus 1 is that there, here. I have the right subscript. I have that. I'm assuming the previous one, so I put it right there. And then the algebra needs to take me to the k plus 1. So the k plus 1, let me put it right here. We want for the pattern to continue, we want 3 raised to the k plus 1 minus 1 over 2. We want for that algebraically to show up by algebra. By algebra on the recursion. So that's what we did. Algebra on the recursion, play with the exponents, and ultimately get that 3 raised to the k plus 1 minus 1 over 2.
understood. Thank you.
My pleasure, my pleasure. Any other questions? Super ultra freedom, total freedom. Ciao.